to look at part 2 of lecture 2. So, this part we'll be looking at the factors that affect biological sensitivity to radiation. So there's physical factors and there's biological factors, and we'll go through each of these. Yeah, I won't read them out here. We'll go through them as we go through the slides. So let's have a look at the first one. Physical factors, linear energy transfer, LET. So we covered this a little bit last week. Whoops, sorry. We covered this a little bit last week when we did the different types of radiation, or the radiation weighting factors in effective dose. Or equivalent dose, I should say. So LET is a measure of the rate at which energy is transferred from ionising radiation to soft tissue. So if it transfers a lot of energy quickly in a short distance, then it's got a high LET. If it takes longer, then it's a low LET. So the unit is the keV per micron there, yeah, that's just the number of keV transferred per micron. A diagnostic X-ray is around about 3 keV per micron, just to sort of set things as our base. Another way of expressing the relative effectiveness of different types of radiation is called the tissue weighting factor. So we did that last week. Like I said, it just comes from different differences in the pattern of energy deposition and the likelihood that it's going to cause a double strand break in the DNA. So the relative biological effectiveness, this is related to the type of radiation. So it's just the dose of standard radiation of 250 keV X-rays necessary to produce an effect divided by the dose of a different radiation source or energy to provide the same effect. So it's just simply a ratio normalised back to 250 keV X-rays. There we go. So we start off here with the radio RBE for diagnostic X-ray is 1, given on this slide here. At this point, low LETs, you can see it's got a slightly less than 1, and as you increase the LET, you'll get an increase in the biological effectiveness. So fast neutrons are around about here, we've got alpha particles up here near the maximum. And that's for the reasons that we went through last week. Here's just a table of the different LET and radiological RBE, I should say, and it's just a summary of them there. And this feeds into ICRP recommendations. So you can see that here we have X-rays of, and all photons are roughly about the same. They're given the same radiation weighting factors when working out the equivalent dose, but you can see that there is a slight variation between the doses. For example, all of these photon type radiations there. Another factor which can affect the biological effectiveness is protraction of the radiation dose and fractionation. So protraction means how long it's drawn out for. So for example, a 2 gray per minute can be lethal for a mouse, like in a minute, but if you give it 10 milligray per hour for a total of 600 hours, it can actually survive with a much higher total radiation dose than a short dose. There is it's a dose rate dependence. The fractionation means if you split a radiation dose into fractions. So if you give short amounts of dose multiple times, you can generally give more total dose than if you give it all at once. So, for example, and the reason for this is there's cell repair and recovery. So, for example, if a mouse survives 2 gray per minute, providing it's not too much of a total dose, in 12 equal fractions of 500 milligray each, separated by 24 hours. So if that total 2 gray per minute dose rate split into small fractions, so 15 seconds it would be, if it's 2 gray divided by 500 milligray, 15 seconds of 2 gray per minute dose rate, a mouse will survive that. The lethal effects of radiation are determined by observing cell survival, not cell death, and this is generally worked out with like cells in a petri dish. So a lot of cells have capacity for a long life and will divide many times. So radiation can cause a loss of this capacity or reproductive death, and then the surviving fraction is given by S here. This expresses the magnitude of the effect of a given dose of radiation. So S is just simply the number of cells surviving a given dose divided by the number of cells in the original unexposed sample. So it's just a fraction. We can have a look at these. We can then use this fraction to look at some cell curves or survival curves. Cell survival curve is often plotted as a semi-log, like this. At low doses, there's this straighter bit up here, where a low dose of radiation can be survived by many cells. And then as you increase, you get this little shoulder area there, and then at higher doses, there's a fairly direct relationship between cell survival and radiation dose. Now we can use that to work out our fractioning of the dose. Get all of the information up there first. Alright, so if we have a single dose of a particular radiation, we'll follow this line down here. But if we split a total dose into multiple short, smaller doses, what you'll see is the shoulder up here comes into effect multiple times, and you can actually get a much higher survival. So if you look at, for example, you're looking at this dose here. So if we give it all, whatever this dose is, and I'm not sure what that's meant to be, if we give it all in a single dose, we're going to get this fraction of cells survive, but if we split it into 2 doses or multiple doses, we'll get this fraction of cells survive. And that's just because of these shoulders up here. For example, say you want to give a dose of 400 rad, and at 400 rad, we can see the blue line here. At 400 rad, you'll get about 0.15 of the cells survive. If we want to give 800 rad, if we just give straight out 800 rad, without fractionating the dose, we will get this amount of cells survive. But if we give 2 doses of 400, we'll get this shoulder again coming into play, and we'll get a higher survival rate here. or actually, sorry, that is the wrong way around. To get that same survival rate, we can actually get give it much more dose. But if you give 2 doses of 400, we'll get this survival rate here. So we'll get a difference between these two here. The type of radiation does come into effect again. So it comes into the LET. We're going back to LET. Oops, excuse me. There's the so we can see the difference here of types of radiation. So we get high LET has a lower survival rate than low LET.